Welcome to my lab on constant velocity. So the purpose of our lab was to observe constant velocity and demonstrate Newton's first and second laws, and this was achieved through observation of an experiment through a program called Tracker and a production of a simulation in a Python API called GlowScript. So the assumptions were there would be no friction or air resistance in the x-plane, and this should have allowed for there to be constant velocity as there was no net force. So the physics concepts we used were the momentum principle, P equals mv, momentum equals mass times velocity. From there we derived two force equations. Net force is equal to the change in momentum over change in time, and the net force is equal to mass times acceleration. And from those force equations we derived the kinematic equations of net velocity is equal to net force over mass times change in time. And also the final position is equal to the initial position plus average velocity times the change in time. So the reasoning for our laws and models. The first law and the second law we use, because first law states that no object will stop its motion unless acted upon by an unbalanced force. Second law connects momentum to force and shows that momentum is, or force is equal to the change of momentum over the change of time, and it's equal to mass times acceleration. The momentum principle states that there's momentum in everything. The first law, we use the first law to show that there'd be constant velocity as long as there's no net force. And we also, the second law was used to actually show that some amount of force will create a velocity of some sort, a constant velocity, because there'd be no more force acting upon it during its reign, or during its trip. So Tracker was used to actually track the observed object in the experiment. GlowScript was used to develop a simulation based on the initial velocity in Tracker. And the assumptions of no friction and no air resistance were to make sure there was no force in the x-plane, so that there's no net force, so the object would have constant velocity. So the preview of the results, we saw a family of similar results in experiment and simulation, and we also saw that the Newton's laws and momentum principle were actually present in our results, and from this we can predict object behavior using object surroundings and the specified laws. So the system, the experiment was done in a lab session, and the mass of the system was the cart. The position where it was on the track was its position, the x position, and hand pushing the cart was the initial impulse or force that acted, that brought the cart to an initial velocity. So the initial velocity was calculated using the first two entries in Tracker, which you can see in the bottom right, and we found the average velocity from those, and that was initial velocity, and then the initial position was also found in the first entry of Tracker. Okay, so in Tracker you can see the object here, the coordinate plane that goes along the track, and a calibration stick that calibrates the whole track and shows that it is a meter long. So if we play this, you can see that the object is tracked as it moves along this track here. And you can also see up in the right-hand corner that there is a whole map of the points that it reaches. And then there's also a whole chart of its position and at what time it reaches that position. The y values here are not cared about because they are too small to matter. After using Tracker, we went to GlowScript, and we used the first entry from Tracker, and then the first two entries from Tracker for the position and the velocity, respectively. The velocity was calculated by getting the first two entries, and then getting the average velocity in between them. And then down here, we also inputted a fraction of that velocity to be incremented for each tick of that while loop in the code at GlowScript. Here you see that the object moves and the simulation works, and we also got a bunch of different numbers that we put into the Excel sheet that I'm about to show you with the Tracker. Here's the Excel spreadsheet. We had a couple iterations of actually putting the data in, but eventually we were able to get this graph over here. We have the times and one little row, the positions in another, and then we have the positions of the observed position as well from Tracker. You notice there were not that many positions here in comparison to the computer. Here's the graph image showing the observed and computed positions of the cart. You can see the computed position had much more displacement than the observed position. So some similarities that, and differences, they both had the same starting point, they both had the same direction, and they both relied on Newton's laws. However, the differences were the difference in speed and displacement, and there was a difference in the number of entries and variation of data, as the observed cart has fewer entries and more variation. Some possible sources for all of this error were changes in observed velocity in the observed cart, because that had friction acting upon it, so it was not perfect like the simulation, which fails to account for this friction and air resistance or air resistance. There's also probably some human error in the tracking, and that led to variation. And there's also few observed entries for the observed cart, and the camera angle may have worsened human error. So what if the axes were altered? Well, the direction and displacement and velocity would change because those are vector quantities, and plus and minus being switching would mean those completely change. The magnitude of velocity, however, would remain unaltered because speed is a scalar. Acceleration is 0, so it would not change even if the signs change because it's constant velocity, at least following the initial impulse or force. The initial impulse slash force would change signs, however, because it's pushing the object in a different direction from the origin because of the plus and minus being changed. However, the magnitude of that force would remain unaltered. Slope would become positive because right now it's negative, so it has to become positive. Can you detect the pushes and pulls on an object? Yes, this is possible because gravitational force pushes the object down, while an equal but opposite normal force pushes it back up. So the zero net force in the y direction, and the x direction there should be no forces, so it should be 0. However, for the case for the simulation, for the observation, there is some friction. So some conclusions that can be drawn from all this are the objects that traveled at fairly constant velocity, and the real-life object was affected by friction while the simulation wasn't. There was fairly similar results in both, and Newton's laws and momentum principle can be seen in both results. And from all this, you can predict object behavior using object surroundings and these laws. Thank you for watching my video.